this video I want to talk about decay equations. We already know that n equals n naught e to the minus lambda t. So we already know that n equals n naught e to the minus lambda t. We also know that a equals lambda n. Okay. Now a is the activity at time t, and n is the number of radioactive nuclei remaining after time t. So these two things are at the same time. Therefore, we can infer that the original activity, or the activity at time equals 0, is equal to the original number of radioactive nuclei, or the original number of radioactive nuclei at time equals 0, multiplied by the decay constant. Okay, so hopefully you can see that's the case. Now, what we're going to do is we're going to take this equation and we're going to multiply both sides by lambda. So we're going to get lambda n equals lambda n naught e to the minus lambda t. Hopefully you can see that this here is equal to a, and this is equal to a naught. And that means that a equals a naught e to the minus lambda t. And this is the second decay equation, and this one's for activity. Okay. Now we can then apply this, or look at this, in terms of a graph. So the activity against time, the activity decreases with time according to an exponential decay equation. So this equation here is the general equation for this graph. Now at time t equals 0, we have activity a naught, and as time goes on, as we said, the activity decreases at a decreasing rate. Okay, so the activity decreases at a decreasing rate. Now, what we can say here as well is we can use this equation, for example, if we wanted to calculate at time t what the activity was. You could take this value for t, put it into the equation. As long as you know the original, as long as you know the original activity and the decay constant, you can then work out that activity value at time t. Okay, so this equation is the general equation for this graph here of radioactive decay, activity against time. Okay.